Good morning. This is Professor David J. De Los Reyes. I will now be discussing lesson number 46 on my subject matter differential equation. I will be giving another example problem on the application of second order differential equation. Okay, I will try to read the problem. Okay, I will check my camera. It's fine. Okay, I will try to read the problem. This is now DE46, lesson DE46, meaning differential equation, lesson number 46. Second order differential equation, application. Another example number 3. Another variation of a problem that involves second order differential equation. Okay, I will try to read the problem. A cable 10 feet long has 5 feet of it on a horizontal smooth roof 15 feet above the ground, with 5 feet of it hanging over the edge of the roof. It is released from rest. How long would it take for it to slide off the roof? Okay, I will try to repeat the problem. We are given a horizontal roof, and this horizontal roof is smooth. So there will be no friction acting on the cable. Okay. We assume the rope to be horizontal. It says the rope is horizontal, so the edge of the rope, we assume it to be vertical. Okay. So actually the angle between the rope and the wall going down is actually 90 degrees. Okay. 5 feet of the rope is hanging. Okay. And what remains on the rope is also 5 feet. The question is, when the cable slides off the rope meaning no more cable on the rope, okay, what will be the total time that will elapse? Meaning the total time consumed by the cable to slide off the rope. So it seems that when the length of the rope is 10 feet, what will be the time t equal to? Because when y is 10 feet, meaning y is actually the variable length of the cable hanging, okay? So when there's no more cable on the rope, the total value of y is actually 10 feet. So it seems the problem is asking, when y is 10 feet, what will be the elapsed time? Okay, let's try to bring out the figure. The figure, this is a horizontal rope, this is a vertical rope, this is 5 feet, this is 5 feet, this is the cable. So as a another presentation for the, what you call this diagram, I will place that the part of the cable that is hanging is actually y, so this y is variable. Okay. The length of the cable that is hanging at any moment in time is represented by y, and this is variable. So if this is y, what remains on the rope is actually 10 minus y. Okay? And the problem is asking, when the total length of the rope that is hanging is 10 feet, what will be the elapsed time? Because when y is 10 feet, the cable is already slide off the rope. Okay, let's try to bring out the pre-body diagram. If we try to cut the cross section of the cable over here, we take the downward portion. It is something like this. This is a cutting plane. I cut the cable over here, so this should be the cable. Then I place the force acting on the cable. The only force acting on the cable as it slides the rope is actually represented by capital letter N. and I place the equivalent of that capital letter F to be equal to delta times y. Delta is actually the linear density of the cable times the length of the cable at any moment in time. So the only force acting on the cable as it slides off the rope is only represented by capital letter F, and this is equal to delta times y. So, but I place it here, delta, okay, is the linear density of the cable in pounds per foot. The unit is actually in pounds per foot, okay? And since later on we need the gravitational acceleration represented by G, this is the gravitational acceleration. Under the English system, this is 32.2 feet per second square. So if we now try to bring out the solution and how to find for there should be an equation of the motion of the cable. And actually that's what you call this number one purpose of differential equation. So by using the equation force is equal to ma, this is one of the equation under Newton's law. The net force acting on a body that is moving is represented by F is equal to ma. Actually, this is summation. Okay? Okay, if we now try to take the summation of the force acting on the cable as it moves downward, it will be delta times y. It is, this is actually F plus F. Or this is F. And what will be the proper sign? The force acting on the cable is goes with the motion, so that this should be plus. Okay? And to compute for this, it is the linear density times the variable length y, and this should be equal to mass is actually weight all over gravitational acceleration times acceleration. This acceleration is different from this. This is due to gravity, and this is the acceleration of the moving cable downward. Okay, so delta times y equal to, if we try to continue, this should be equal to the total weight of the cable. Since the length is 10 feet, the total weight of the cable should be the total length times its linear density. Okay, all over the gravitational acceleration 32.2, and the acceleration of the cable is the variable length over here is y. So if we try to take the second derivative of that y, that represents acceleration. This is actually acceleration. Okay? Left hand side, right hand side, this is delta, this delta, actually it cancels out. Okay? We do not need the exact value of that linear density. So if we try to manipulate the resulting equation, d square y over dt square, okay, we want to remove this 10 over 32.2 for the coefficient of the first one to be unity, or just simply 1. So 32.2, it will go here till we divide it by 10, it will become 3.22. Since this is on the left hand side, we transpose 8 on the right hand side, then we rearrange. What will come out will be d square y over dt square minus 3.22y. This is minus, okay, because this is plus, okay, and this should be equal to 0. So what comes out is the variable function y in time, and this represents our second order differential equation. That's why our topic for tonight is second order differential equation. Okay. Under the second order differential equation, this is the solution. We let y equal to k e raised to mt, dy dt equal to km e raised to mt. The second derivative is actually, we take again the derivative of this. It is km square e raised to mt. Then we try to take this value y, and the second derivative we place back here on the SODE, meaning second order differential equation. I will check again the camera. Okay, we take these two values here, we place it back here on the SODE. After the substitution, what comes out is km square e raised to mt minus 3.22 k e raised to mt equal to 0. And if you notice it, there is a common factor for both the first and second term. Actually, that is a k e raised to t. So actually, we could cancel this one. We could cancel this one. Okay? We could remove this one. It's a common factor, right? What comes out will be an m squared minus 3.22 equal to 0. And under second order differential equation, this is termed to as characteristic equation. It is the characteristic equation of the roots of the solution. So if we now try to compute for the roots, m squared will be equal to 3.22 after the transposition. M now will be equal to, if you try to take the square root of both sides, okay, this is now laws of exponents. This is now an application of our knowledge of algebra. M squared raised to the 1/2, these two here cancel with this, right? So it will become M. And 3.22 raised to the 1/2 is just square root of 3.22. A radical sign without the 2 is square root, right? Square root. But if this is 3, it should be cube root. I am just telling this one because something on, you like, I know for a fact that others made a mistake on this one. So if the factor, number 2 here is missing, it is square root. If it is 6, it is not square root. It is 6 root, okay? But for this, it is square root. So m now will be the square root of 3.22, and luckily, the sign of the term inside the radical sign is plus, so the roots will be a real number. And if you try to take the square root of 3.22, that is 1.794. And this is preceded by plus and minus. Okay, so M1 is the positive 1.794 and M2 is the negative 1.794. And this falls under case number 1. Under second order differential equation. Case number 1. The roots are actually real and not equal. They are not equal because this is plus and this is minus. If you try to take the absolute value, they're equal. But since this is plus and this is minus, they are not equal. So it falls under case number 1. The roots are not equal and they are real. Okay, so this falls under case number 1. So the solution should be y. This is d square y, right? So the solution will be y. We are now taking the equation of the motion of the cable as it moves onward. K1 a raised to m1t, which is 1.794, plus K2 a raised to negative, this is negative, 1.794t. We are just substituting the computed values of M1 and M2, right? So we are now given a, what they call this, general solution. This is not yet usable to compute for time, because to compute for time, we should know the value of K1 and K2. Okay, let's try to bring out the initial condition. At time t equal to 0, the length of the cable that is hanging is only 5 feet, right? It's 5 feet initially. So at time t equal to 0, y is 5 feet. Okay, so this should be 5. We'll follow this, substitute this condition here. You should be equal to K1. At time t equal to 0, 1.794 times 0 will be 0, and a to the 0 will be 1, so this is times 1. Plus K2. At time t equal to 0, this will become 0. Negative 1.794 times 0 will be 0, and a to the 0 will be 1, so this is times 1. So our first equation will be, this is now algebra, okay? We bring out, or we brought out a linear equation involving K1 and K2. Okay, that's why I told you the prerequisite is algebra. One of the prerequisites is our knowledge of algebra. So simplifying this one, K1 plus K2 should be equal to 5. And I will let this one as equation number 1. Why I let this one as equation number 1? Because for the meantime, we do not know the value of K1 and we do not know the value of K2. So to compute for the value of K1 and K2, let's try to bring out another relation involving K1 and K2. Okay, and to bring the other relation, we will take the derivative of the general solution. dy dt will be equal to, the derivative will be 1.79 for K1 e raised to 1.979 for t. Because if you try to take the derivative with exponent, it will be 1.794 times 1 times K1. So this is 1.79 for K1 e raised to 1.79 for t. And for the second part, it should be K2, and the derivative of the exponent is negative 1.794 times 1. Negative 1.794 times K2, this should now become negative 1.794 K2, okay, e raised to 1.794 t. Okay? We need this equation to bring out another relation involving K1 and K2. At time t equal to 0, okay, dy dt equal to 0. Okay? It starts from rest. When the length of the cable that is hanging is 5 feet, the initial speed is 0. So I place it here at time t equal to 0, dy dt is equal to 0. So using the first derivative, this should now be equal to 0. 1.794, I'm following this. 1.794 K1. At time t equals to 0, this will become 1. So this is times 1. Minus 1.794 K2, I'm following this. This will become 1, so this is times 1 also. And if you try to simplify the resulting equation, there's a common factor 1.794. Okay? Actually, we could remove those ones. But the second part is negative. So K1 will be equal to K2. This will be equation number 2. This is now the second relation involving K1 and K2. And since we are given two simultaneous linear equations, we could compute for K1 and K2. So if we place K1 to be equal to K2 or K2 equal to K1, back to equation number 1, K1 plus K1 equal to 5, or 2K1 will be 5 over 2, and that is 2.5. And since they are equal, K2 should also be equal to 2.5. Okay? I will check my camera. Okay, I will continue here. So y now will be equal to, okay, I will better place it here. It's at the bottom. You might not see it. So we now know the value of K1 and K2. So the resulting particular solution will be y equal to, we are following this one. K1 is equal to K2, right? So what is 2.5? It is 5 over 2. A factor out. Okay, so what remains inside, if I will try to follow this, e to raised to 1.794 t plus e raised to negative 1.794 t. Okay, I will try to remove this 2 here. I will place it inside. Okay, close quantity. So after the substitution of the value of K1 and K2, we are now given y as a function of time. And the problem is only asking, when y is equal to 10 feet, what will be time? When y is 10 feet, the cable is already dropped off the roof, okay? And what the problem is asking, what will be the total time that will elapse? It's just now a matter of substitution. So 10 will be equal to 5 times. This function here is actually hyperbolic cosine. This is hyperbolic cosine of e to the 1.794 t. The equivalent of e to the u plus e to the minus u over 2 is actually hyperbolic cosine. Okay? So divide this by 5, divide this by 5. So what will come out will be 2 equal to hyperbolic cosine of e to the 1.794 t, right? To compute for time, we must have to eliminate this hyperbolic cosine. Taking the hyperbolic cosine, inverse hyperbolic cosine of the left-hand side, it is written like this. Hyperbolic cosine to the negative 1 of 2 equal to hyperbolic cosine to the minus 1 of hyperbolic cosine. Actually, this is plus 1 times e to the 1.794 t. Okay? This is minus, this is plus, they try to cancel out. Right? Therefore, is it correct? This should be, sorry for this one. It's only 1.7940. Okay? No more E. It is only 1.7940. Okay? And this is 1.794T. Since this cancel out, T now will be equal to inverse hyperbolic cosine to the minus 1 of 2 all over 1.794. And using your calculator, the inverse hyperbolic cosine of 2 using your calculator, okay, what will come out will be 1.317 all over 1.794. After the division, the total time that will elapse for the cable to drop is actually 0.734 seconds. 0.734 seconds. So this is our final answer. You got it? You know how this was simplified? Because after the substitution of the value of Q1 and Q2, okay, we place Y equal to, this is actually 2.5. I make this 5, then I put 2 here because 5 over 2 is 2.5, right? But if you try to recall, hyperbolic cosine of u is actually e to the u plus e to the minus u over 2. Okay? That's the equivalent of this one. So actually we simplify it. Instead of working with the exponent, the equivalent of e to the 1.794t plus e to the negative 1.794t over 2 is actually hyperbolic cosine of 1.794t. That's hyperbolic cosine. Okay? So hyperbolic cosine, so eliminate this hyperbolic cosine here. Take the inverse hyperbolic cosine. The inverse hyperbolic cosine of 1.794t is equal to the inverse hyperbolic cosine of the left hand side. This is minus, this is plus, they cancel out. Okay? So what remains is 1.794t equal to inverse hyperbolic cosine of 2, and solving for t will be the inverse hyperbolic cosine of 2 all over 1.794. Okay? You display to here hyperbolic cosine of 2 is 1.317. Okay? 1.317 over 1.794, this should be 0.734 seconds. So that is the total time consumed by the cable to totally drop off from the roof. Okay, that's it, guys. That is an example problem of a pulling cable from a smooth roof. The rope is smooth, right? We got the cable over here. This is smooth. So if the rope is smooth, there will be no friction acting on the cable. So this is actually zero. Because if there is friction, okay, even on the wall, our equation will be different because this F here, we will subtract by the frictional force over here. If there is, but the problem says it is smooth. So it's the only force acting on the cable is actually the total weight hanging. Okay, no more friction. Okay, that's it, guys. So for those who are taking up differential equation, this is for you guys. If you like it, please click like. If you want to subscribe to my channel is actually at youtube.com/@ProfDavidJ.Reyes. If you want to share it, please click share. Good evening, Los Angeles.